Hello everyone, this is Hao Chen from Alibaba Cloud. This paper presents a cloud-native database ensuring low latency for strong and consistent reads, namely PoloDB SCC. It's already commercially available at Alibaba Cloud and is serving for many customers. Cloud-native databases are becoming a critical infrastructure supporting the migration of data storage and processing tasks to the cloud environment. Many of them adopt the disaggregated shared storage and usually consist of one RW node to process the read and write requests, and one or more R nodes to handle read requests. To keep an R node's in-memory data up to date, the RW node generates the corresponding log for each update and ships the log to R nodes. Then R nodes apply the log to update their in-memory data. Since the log application process is asynchronous, an R node may be unable to return the latest updates that have already taken place on the RW node, and consequently may return their data. Many cloud-native databases claim that R nodes could improve read performance. However, the R node can only serve applications that does not require read-after-write consistency. In the next slide, we will show the results from some commercial cloud-native databases. This table shows the stale read ratios of some databases. The stale read ratio means how many read requests get the stale data on the R node. In this test, we first update the record on the RW node, then read it from the R node after delta time. It shows that only PoloDB SCC can completely avoid the stale read. In other databases, if the delta time is 1 millisecond, almost all read requests get the stale data. Even in the PoloDB without enabling SCC, the stale read ratio is still high. In this case, applications that require strong consistent reads have to send the read request to the RW node, making the R node idle most of the time. So R nodes are only used for handling failover, but not for scalability. And the resources on R nodes are not fully utilized. In this figure, we sampled the CPU utilization and read throughput of RW and R nodes from a PoloDB instance at Alibaba Cloud. From this figure, we can find that the RW node's throughput and CPU utilization are up to 50 times higher than the R node. There are also some solutions for strong and consistent reads on R nodes. Commit wait and read wait are two straightforward designs. In the commit wait approach, the RW node has to wait for the related log to be applied to all R nodes before committing a transaction. The read wait policy requires an R node to get the RW's current timestamp when a request arrives and wait for the logs that happens before that timestamp to be applied before processing this request. This two-naive solution induces expensive wait time and sacrifices performance significantly. Some systems do provide these operations for ensuring a strong, consistent read, but they are not recommended due to their poor performance. In the PoloDB, if we simply use the read wait policy, the R node's latency will increase by more than 100%. To achieve low latency for strongly consistent reads on R nodes, we propose the PoloDB SCC. This figure shows the architecture of PoloDB SCC. The core components of PoloDB SCC are the hierarchical modification tracker, linear Lamport timestamp, and the RDMA-based log shipment protocol. Linear Lamport timestamp proposes a scheme to process a batch of requests by using one-time timestamp fetching. This saves a lot of overhead on timestamp fetching. The hierarchical modification tracker maintains the RW node modification timestamp at different levels. This allows R node to wait for log application at a fine-grained level, thus avoid unnecessary wait. To minimize the network overhead, we fully utilize the RDMA network in PoloDB SCC. The timestamp fetching and log shipment are both done via one-sided RDMA interface. We will discuss more details about these designs in the next few slides. We first introduced the linear Lamport timestamp. It's designed to reduce the timestamp fetching operations. The vanilla read wait scheme requires each read request on the R node to fetch the RW node timestamp before the actual execution. Actually, if a request finds that someone already fetched a timestamp after its arrival time, it can directly reuse it instead of fetching a new one, which can still guarantee strong consistency. We use a demo to prove this. There are two requests on the same RL node. Request 2 starts fetching the RW node timestamp at T2 and gets the response with RW's timestamp at T3. Then we can get the happen before relation. E2 happens before TSRW and TSRW happens before E3. The other request R1 arrives at the same R node at T1 by assigning a local timestamp for each event that happens on the R node. If E1 happens before E2, we can infer that E1 happens before E2 and E2 happens before TSRW. TSRW happens before E3. So in this case, TSRW could reflect all updates that happened before E1. As a result, R1 can directly use the timestamp TSRW. So we can conclude that a request can reuse a timestamp which is fetched after its arrival time. Based on this theory, we can catch the RW node timestamp on the R node and conditionally reuse it for some requests. To implement this, whenever R node fetches the RW node timestamp, it will catch this timestamp locally with the fetch operation's completion time. Another important design of PolarDB SCC is a hierarchical modification timestamp tracker. On the RW node, it maintains the modification timestamp at the global level, table level, and page level. The global modification timestamp means the current commit timestamp at the RW node. The table and page level modification timestamp represent the corresponding table and page's latest modification timestamp. They are all stored in the memory at the RW node. The timestamp can be fetched by R node via our RDMA interface. For example, there is a query to select table T1 on R node. The R node first fetches RW timestamp to compare with the local timestamp. If it's not satisfied, the R node will not wait for the log application immediately. Instead, the R node will further check the access table's timestamp. In this example, it will fetch T1 timestamp from RW node and compare it with the local timestamp. If the table's timestamp is still not satisfied, it will further check the page level's timestamp. The R node will only wait for log application if the page level timestamp is not satisfied. During the processing, once the level's timestamp is satisfied, it will not check the next level timestamp. With this design, in the worst case, the R node only needed to wait for the accessed pages instead of waiting for the global timestamp. It can avoid the unnecessary waiting time. Last but not least, PolarDB SCC is highly co-designed with the one-sided RDMA interface. The timestamp fetching and log shipment are all done via one-sided RDMA interface. This not only reduces the latency, but also saves the CPU cycles. It makes a significant contribution to the performance in our evaluation. Since PolarDB SCC is in production and commercially available at Alibaba Cloud, our evaluations are all conducted in the PolarDB cloud environment. Because PolarDB SCC is implemented in PolarDB, PolarDB is the natural baseline. We configure PolarDB in 3 ways to compare with PolarDB SCC. In the default configuration, it handles all the read and write requests on the RW nodes. In the read-wait configuration, the R nodes use the vanilla read-wait scheme to achieve a strong, consistent read. Stir read configuration means R node directly processes the read request without waiting for log application. It may return stir data. Furthermore, we also compare PolarDB SCC with 2 commercial databases and the MySQL group replication. We run Sysbench, TPCC, TATP, and the Alibaba production workload to evaluate the performance. Due to the time limit, we only discuss a few sample results in the next 2 slides. This figure shows the performance with Sysbench read-write workloads. It indicates that PolarDB SCC always has similar performance, both throughput and latency, to PolarDB stir read under different workload pressures. This is because our careful designs. When the workload pressure is light, like 60 or 32 threads, PolarDB default performance is nearly identical to others, but it becomes saturated at 64 threads and performs worse than PolarDB SCC and PolarDB stir read, because there are nodes to help process read requests. PolarDB read-wait throughput is even worse than PolarDB default at 16 threads, because its RW node is not saturated, while its R node induce extra overhead. From this figure, we can conclude that PolarDB-SCC achieves strong consistency, but its performance is nearly close to the steroid configuration and significantly outperforms the other configurations. PolarDB-SCC can provide a unified endpoint, for example, via proxy, that promises strong consistency for applications. Users can connect applications to that endpoint and increase or decrease the number of R nodes at the backend without any change to applications. They only need to pay for the necessary R node resources to achieve high performance. PolarDB's serverless feature has the ability to dynamically adjust the number of R nodes for dynamic workloads. Integrated with PolarDB-SCC, the application seems connected to a single RW node with dynamic resources in the background, which guarantees strong consistency. We test this scenario as shown in this figure. The workload becomes heavier at 300, 600, and 900 seconds. The database cluster will dynamically add more R nodes in the background, and the throughput is quickly improved in an almost linear fashion when more R nodes are added to the cluster. To summarize, PolarDB-SCC is designed to achieve low latency for strongly consistent reads. Thank you.